Welcome. In this podcast, we're just going to review through our polynomials and some of the key concepts that we've learned in these series of lessons. All right, so we can start off with our constant polynomial function. That's just a horizontal line. I have all this information up here already. I'm just going to kind of go review it with you, and I think you might have it already in your notes. A horizontal line has no turning points, right? It's just a line. It doesn't change directions, right? It's a single horizontal line, right? It has no zeros because it never crosses the x-axis, right? So no x-intercepts or solutions. We move up one to a linear polynomial function, right? So example equation, of course, is our in slope-intercept form. F of x equals mx plus b. You know what? I'm going to create a little arrow here. Hopefully it'll all stay together. As it does. Okay, then you know where I'm talking about because I'm going to point to it. All right, so we have one x-intercept. Right, so since it's x to the first, degree is 1, it will have one x-intercept, right? It has to cross the come on, arrow, come on along. Has to cross the x-axis somewhere, right? So there's our one x-intercept. But notice again, it doesn't have a turning point. Right? It's a line. It can't turn around. Moving up a degree to second degree. So now we're at degree 2, and it has a maximum of 2 zeros, 2 x-intercepts. Right? So notice that your zeros match your degree. Right, so we our standard form, our f of x equals ax squared plus bx plus c. Remember, we had other forms too, though, right? Vertex form, f of x equals a times x minus h, all squared, plus k. And then hk was your vertex. And then we also had intercept form, was all factored for us. So our maximum number of zeros is 2, but we can have 0, 1, or 2 x-intercepts. So we're always going to have 2 solutions. Right, and the most number of times we can cross the x-axis is 2, but always 2 solutions. So if we have no x-intercepts, that means both of those solutions, they were complex solutions. If we have one x-intercept, that means that x-intercept is also our vertex, and it appears twice. It's multiplicity 2. If we have 2 x-intercepts, they're both multiplicity 1 because that's all we can have. And of course, our graph is going to have, okay, move my hand now. It's going to have one turning point, and of course, that turning point is right there. It's our vertex, right? So maybe I can take my well-drawn, beautiful arrow with me if I can copy it. Oh, look at that! It's going to let me copy it, not be a problem. All right, so let's put it over here. Whoop. Yeah, we're on the right page, I think. Yes. Almost seemed like we changed pages. All right, so now we're at the cubic functions. Its degree is 3. It can have 3 maximum solutions. All right, and we'll talk about how many. So maximum number of x-intercepts is 3. It'll always have 3 solutions, but maybe not 3 x-intercepts. All right, so if you're a cubic, your largest term, your term with the largest exponent, of course, is going to be a cube. And you could have any one of these other ones along with you. Right, so we can have either 1 x-intercept, 2 x-intercepts, or 3 x-intercepts. So how can we have 1, 2, or 3? Well, but we know it will never have 0. Never, ever. It has to cross the x-axis somewhere, right? Because the ends go different directions. So it has to cross the x-axis. You can have 1 x-intercept 2 different ways. Either it's multiplicity 3, it occurs 3 times, like for instance the equation y equals x cubed. We have 3 zeros, right? The only thing that's going to make x cubed equal to 0, of course, is 0. And you have that 3 times. Or you can have 1 x-intercept, and then you have 2 complex solutions. If you have 1 x-intercept and 2 complex solutions, your graph is going to just turn somewhere randomly and not at like this one is where it's turning after an x-intercept. It's going to turn someplace else. And we saw one of those many podcasts ago. We can have 2 x-intercepts if one of those x-intercepts is repeated. remember, and then we'll touch and turn. Or we can have 3 x-intercepts if they're all multiplicity 1. Oh, by the way, here's our cubic graph. This is the one that would have multiplicity 3, right, because it's got 3 zeros, y equals x cubed. All right, so those are all the possible combinations of x-intercepts we can have, but there's always 3 solutions. The most number of turning points is 2, right? Maximum 2 turning points, right? You have to have one less turning point than x-intercept, right, because you have to turn in between those x-intercepts. Quartic polynomial function, right? So we're going to have something to the 4th power. It's a 4th degree because it's got exponent of 4, right? So degree 4. Maximum number of zeros is 4. There's all kinds of ways though we can have. So we can have as many as 4 x-intercepts. We always have 4 solutions. And here's all the different ways they can occur. We can have 0 x-intercepts if all 4 are complex. And that is possible. We'll have 1 if it's multiplicity 4. Like for instance, y equals x to the 4th. It's got the only 0 is 0. And it occurs 4 times. Because you're setting x to the 4th equal to 0. Or you have 1 multiplicity 2. And then 2 complex. Complex always have to go in pairs, plus or minus. You can have 2 x-intercepts if they're both multiplicity 2. Right? You have 2, and then so you've got 2 x-intercept. You have 2 with multiplicity 2. Right? Or you can have 2 with multiplicity 1, and then 2 complex. So these are 2 different ways here. So 1 is that you've got 2 x-intercepts and they're both multiplicity 2. And we had that when we had one that looked like that real symmetrical W where both of them touch and turned, right? Negative 1 and 1. Or you can have 2 with multiplicity 1 and then 2 complex. And then it's going to do a strange turn in between somewhere, not an x-intercept. Or you can have 3 if one of them is multiplicity 2 and 2 of them are multiplicity 1, then you'll have 3 x-intercepts. Or you'll have 4 if they're all multiplicity 1. So there we go, all the different ways we can put those together. All right, so we're going to move on. So now we've looked at our basic ones. We really will not be doing much with anything to the 5th power. I'm not going to ask you to graph it. Numbers grow pretty big on that, but maybe we'll just talk about increasing, decreasing, or the x-intercepts when you already have a graph. But we're going to focus mostly on cubic and quartic. So a reminder of polynomial end behavior. We're considering what happens when x gets very large in positive and negative directions. I generally call it end behavior, though it can be called long run behavior. The term that determines it is your leading term, right? And the leading term is the one with the largest exponent. We have 4 possible scenarios. If it's even, right, ends have to go the same way. I want my arrow back. So even, come back down again. The ends have to go the same way, right? If the leading coefficient is positive, both go up. If it's negative, they both go down. Right? And then here we have, and we have an arrow that just goes wherever it wants to. And there we have our 2 different types of end behaviors, right? And in both cases, the ends are going to go the same direction, right? So y is going to go to positive infinity, right? If your leading coefficient is positive, regardless of whether x goes to negative infinity or positive infinity. And then it's going to go to negative infinity if your leading coefficient is negative, regardless of whether x goes to negative infinity or positive infinity. And if you need to review end behavior, we did a whole lot on that when we were talking about the shapes of the graphs. And then here, if it's odd degree, your ends are always going to go in opposite directions, right? If your leading coefficient is positive, it's going to go up left to right. If your leading coefficient is negative, it goes down left to right. Remember though, that's if you're asked about end behavior, that's not your end behavior, right? You need to tell what f of x or y is doing as x goes to positive infinity and negative infinity. And you have all that in your notes. So nice in one of the lessons. All right, so now we're going to continue on. We've looked at end behavior. Almost done with my review. Right? I think there's just 2 more pages. So turning points on a polynomial function. Let's get my little arrow back. Who's helping me here? Such a beautiful arrow. So a turning point, I'm reading right up here above the arrow. A turning point of a function is a point where the graph of the function changes from sloping downwards to sloping upwards or vice versa. So the gradient changes, and gradient is another word for slope. Right? So the slope is going to go from negative to positive or positive to negative. Right? So in other words, it's going to go from wherever we have a turning point, it's going to change. It's either going to go from increasing to decreasing or decreasing to increasing. And our polynomial functions are going to have n minus 1 turning points, where n's your degree, right? So the number of turning points is 1 less than the degree. So this is degree 2. It's got 1 turning point, right? Decreasing, because y goes down left to right, and then increasing, y goes up, right? So here it's going, the y values are getting smaller, and then they're getting larger. Right? So cubic can have up to 2 turning points. Right? So here this one has 2. It has a relative max and a relative min. Right? So here our graph is increasing. Right? And then right here at our turning point, it's decreasing. It has to do something at a turning point. It's turning. Right? And then here at the next turning point, it changes again, and now it's increasing. Some cubic functions, though, have fewer turning points. So, for instance, this one here, no turning points. It just keeps increasing. This is x cubed. Just keeps increasing. In the same way, quartic can have up to 3 turning points, and it would look something like this, although some can have less. So here we are decreasing, and then we're increasing. So then here's our turning point. That's a relative min, and then we're increasing. There's a relative max. So then we're decreasing, and there's a relative min, and then we're increasing, and we'll just keep doing that forever and ever and ever. And ever. And then, finally, this is the last page. Some key ideas, right? I don't think my arrow is going to be able to move fast enough. And you now know that I did not remember to plug in my computer. At 16%, that's fine. Actually, maybe I'll put my arrow back. All right, so you can sketch a polynomial graph using the x-intercepts, the y-intercept, and the degree of the function. The sign of the leading coefficient gives you the end behavior. And of course, don't forget your relative extrema. Those are your turning points. The x-intercepts of the graph of polynomial function are the roots of the corresponding polynomial function. And our turning points are always in between those. When a polynomial function is in factored form, you can determine the zeros from the factors. When it's not in factored form, right, you can use the rational root test and then division, or you can use substitution, or you can do factoring by grouping or pulling out a greatest common factor. And they're all listed right here where my arrow is pointing. When the factor is repeated, right, that is our multiplicity. Right? So however many times it's repeated, that's what your multiplicity is. And if it's even, it's going to touch and turn. And if it's odd multiplicity, cross. I have it right down here. So odd multiplicity, it's going to cross. And even multiplicity, touch and turn. And I'm going to skip this here because I'm just hitting the key ideas here. So polynomial functions change signs at x-intercepts. Right? Anytime the 0 is an odd multiplicity. So in other words, it's going to cross and go to the other side. It's going to cross the x-axis. So right here. Woo! Right? So here we crossed from the positive to the negative, right? Because that only occurred once. And then our turning point, we turned around again. And it looks like we just keep on increasing here. There's no more turning points. Right? So turning points are always in between x-intercepts. And guess what? I've hit the key ideas that I wanted to hit. And that's the end of my podcast. So bye for now, and thanks for watching. And my arrow says goodbye too.